Then it becomes Monday morning. And today we will finish the first order differential equations we've been working on. That means next time we will start on second order differential equations. And when we finish that, the biotech students will be done. So the biotech students have today, and then maybe 2 more times, and then we are done. And then you can start studying for the exam. I've now remembered to post the oral questions, but we are currently working on first order linear differential equations. And a first order linear differential equation looks like this: y prime plus some function f of x times y equals some function g of x.
So if something could be written on here
Magic
with
shape
that,
here. So we'll call it mouse
so
first.
close. Then you can see how it looks.
And here's a function, and here's a function. These are known in advance, so they are not what you need to find when solving the differential equation. What you need to find instead is a function y that depends on x, such that if you differentiate y with respect to x and multiply it by that function which was given beforehand, you should get that function for any value of x. And up here, I've given you a warm-up exercise, which has exactly that mathematical structure, because you can see that the function here called f of x is right here. And the function that is on the right side, which is g of x, stands here.
And that is
because
why
it has that structure, you can use the solution formula we provided, which is the standard formula. And the universal formula said that the complete solution y of x for this differential equation is equal to Euler's number raised to the power of the negative antiderivative of f, and then multiply by the parentheses. And then it is the integral of g of x, multiply Euler's number raised to the antiderivative of f, and then you must remember to write plus k to get all the solutions. So we just plug it in, and then we can find the solution. So let's try it. What do we get? We get Euler's number raised to the power of negative integral of 1 over x. But which function, when differentiated, gives 1 over x? Well, that is the natural logarithm of x. And note that I have kindly mentioned here that x is greater than 0. So you can take the natural logarithm of x, so there doesn't need to be any numerical sign, because I have limited the differential equation to looking for solutions, but only solutions where x is positive. So therefore, it should just say e to the power of negative natural logarithm of x here, instead of e to the power of negative capital F. And then I need to start on the parentheses. The integral is g, and g is x squared. So I get x squared times e to the power of plus ln x. Now you can see the same, just with the opposite sign. And then we finish with the symbol dx after writing an integral sign. And here one must be careful, because one might be tempted to say that e and n just cancel each other out since they are inverse functions. They are indeed inverse functions, and they do cancel out, but not in the simple way one might think, like just crossing them out. One must rewrite this using a power rule to this: e raised to the natural logarithm of x, all raised to the power of negative 1. If you do that, you must cross them out. And then there remains x to the power of negative 1. And then multiply, so I've just written it out again here. X squared times e raised to the power of ln x. But they cancel out, so it just gives x. So what we have now is apparently x to the negative 1. Multiply, and then we need to solve this integral. And if I need to integrate x cubed, which this gives, it indeed gives x cubed. When I multiply x squared by x, I get 1/4 x to the 4th. We have learned that this is the antiderivative of x to the power of 3, and then plus c. And if I then multiply inside the parenthesis and multiply it by the first term, what do I get? Well, then I get 1/4 x cubed. Because I have to add the two exponents together. And when I multiply it with that one, I get k times an additional part. And here we know that x must be greater than 0, and we know that k can be anything. So here's the solution.
that is the solution. Are there any questions about it?
So we have learned that when an equation is linear, It has the same solution structure as what we called linear equations when we studied linear algebra. And this means that there are two parts in the solution. What is one part? It is a particular solution to our differential equation. And that is the first part mentioned here. And the other part over here is what solves the corresponding homogeneous equation. So it corresponds to the kernel of the mapping. So this one over here is the one with the free parameter. Remember, when you had a solution with infinitely many solutions, it was t times some vector. Here, k acts as t. So k is like the free parameter. When k goes through all real numbers, we get all the solutions to the differential equation where there is 0 over there. That's what we call the homogeneous version. So the homogeneous version will look like this. The homogeneous version is the one where it says y prime plus 1 over x
E equals 0.
And what is at the end, which is called k times x to the power of -1. That is the solution to that one. So here is the solution to the homogeneous equation k times 1 divided by x, where k can take any real number. And what is written here, 1/4 x cubed, what does it solve? Well, it is just a specific solution. That is a particular solution to the entire equation. So the original differential equation, which is called y prime plus 1 over x times y equals x to the power n. Here we have a particular solution, which is 1/4 times x cubed. So that is one solution to the equation. That is not all the solutions.
That is all the solutions to the homogeneous.
And how do you find all the solutions to the original equation? That is to this one. You can simply do that by adding the two together. So the complete solution, y, the complete solution, now I call it yf for complete, is just the sum of the two. It is the sum of the particular solution and the complete solution to the homogeneous. And that is the solution structure. There's a linear differential equation. And that's why we call them linear, because they satisfy the same nice linearity conditions that we've learned about in linear algebra. Any questions about that? This one is because if it equals 0, you get a special version called the homogeneous version. And the reason why I did this, the reason why I showed you what happens if there's a 0 there, was because it was the same as what we saw with similar and equation systems. So maybe I should take an example so you can remind yourselves how it was with those similar and equation systems. So if I now have a linear equation system that I am just coming up with here to describe it, it could be that I had two equations with two variables. Here is equation 1, 2x plus 3y, or 1 times 4. So when it's Monday morning, you choose the numbers 2, 3, 4, and then I have another one, which is 4x plus 6y equals 8. And for those of you who are awake because you've had your morning coffee, you'll notice that the bottom equation is just a repetition of the top one. It's just multiplied by 2. So it's linearly dependent. What does that mean? It means that there aren't two different equations with two variables. There is one equation with two variables repeated twice.
And what is this again? Oh yes, it's a straight line.
That is the direction that has the normal vector with coordinates 2 over 3, and which passes through a point with some coordinates. For example, one could find it by setting y to 0 and then finding x. So if x is 2 and y is 0, then we have a point that enters.
Where it's hidden, similar.
So that means when I try to solve it by writing up the total matrix, I find that it does not have full rank. Because it does not have full rank, there are infinitely many solutions. Let's just try to do it. The total matrix looks like this.
2, 3, 4, 6, and then a right side called 4, 8.
And then I can take
I can take row 2 and subtract row 1 twice from row 2.
-2 times rocket. Then I get 2, 4.
Bathroom scale 3.
And when I take it -2 times it, I get 0. And when I take it -2 times it, I get 0. And when I take it -2 times it, I get 0. So I get a 0 row because the two equations are isolated and dependent.
Then I can stretch the times through by 1/2.
So I get the leading one that can appear there, and then I get 1 3/2. And when I divide this by 2 or multiply by 1/2, I get 2. And here I still get my goose egg.
So you can see I could only get a leading one.
So the best I could come up with is that 1 times 1 plus 3/2 times x2 should be equal to 2. So let's go up.
1 times 1. And now it is no longer called x1. It is just called x plus 3/2.
Normally it can be called x2, but now I've decided to call it y. Then I gave them both.
And there you can see here that
I can introduce y as a free parameter because I cannot find x until I know y. So you could say that x depends on y. So y is called t. So if I just call yt, then it says here that x is equal to 2 minus 3/2 t. Can you see it if I isolate x in this equation and replace y with t? And now I can write how my solution looks in standard parametric form. It looks like this. X over y is equal to some fixed point plus t times some vector.
That's how it looks from the outside.
It was supposed to be called 2. So there should be 2 numbers there, but y is only t, so there should just be a 1 there. And x also involves negative 3/2 t, so negative 3/2 should be up there, and then 0 should be there. Now it matches. What is x equal to? 2 plus negative 3/2
10.
t. That was it, I stood there.
And what is y equal to? Y is equal to 0
Plus tax.
and
So
that's
right
all.
with 0 plus t. That fits.
So what we have discovered here is the general solution tour of your systems of equations. This here is just one solution. That one, it is one particular solution, xp, for your systems. Look here, if I set x to 2 and y to 0, what do I get? 2 times 2 is 4, plus 3 times 0. Is it true that this equals 4? Is it true? Then it satisfies that part. If you set x to 2, then it says here 8 plus 6 times 0, that is 8. Is it correct that it's equal to 8? Is that good? So we can see that this is a specific solution to the equation system. So what is this? This is the complete solution to the system of equations if it had said 0, 0 over here. So if it says 0 over there, then it will be lit. And you can try to see, choose t as some random number. For example, set t to negative 2/3. If I set t to negative 2/3, it will say negative 2/3 times negative 3/2. That must give 1. So this results in getting something called 1. If I set t to minus 2/3, then it's just minus 2/3. So it doesn't turn out as nicely as I'd hoped. But those two numbers will solve it if there is a 0 over here. You can just try it. Try setting x to 1. Then it says 2 times 1, which is 2. And then plus 3 times negative 2/3, which is negative 2. It says 2 minus 2. That is 0. So you can see it solves to show 0 there. This vector. And it's the same down here. And no matter which TV they had chosen, I would still give 0 over here. So because it does not matter which TV I choose here, would have given 0.0 over here when substituted in. So this is indeed the complete solution to the corresponding homogeneous line. And that is exactly how solutions behave for lines and line systems. It is always their structure, and that is why we call it the structure theorem. The solution has what structure? A particular solution for the line system itself, but only one, plus the complete solution to the corresponding homogeneous line system. And that's exactly how that differential equation behaves. What is the solution to it? It's a single solution to the differential equation itself, plus the complete solution to the corresponding homogeneous equation, where there's a 0 on the right side. And that's why we call such a differential equation linear, because its solution structure is in the same way as for linear equations. And in fact, you can think of functions as entities that exist in a vector space, but theoretically, we have not delved into the foundation. Wait, what do you mean? Benjamining. What it says x0 has nothing to do with what I just talked about. This is a condition I set on which range x can vary. It doesn't have anything to do with the actual structure.
Thank you for listening.
So yes, you still have to rate it. Even if it says it's not greater than 0, you still have to.
Look at the homogeneous differential equation to understand the solution structure.
All right, let's now review some of what you have had, so you can prepare again. Then there will be something new called the superposition principle and the guess method.
So here comes board 2.
Yes.
I think you can sense that differential equations only become easy when you are really good at differentiating and integrating, because otherwise it's actually really difficult. So if you feel like you come across something you can't remember now, there's time to go back and watch the videos we made on differentiating and integrating again, just to really hammer it in.
Now, so what was it we have had?
Let's just go over it again. We looked at a differential in 1 that has this castle. When it has that form, we call it first order and resembles with variable coefficients. And then we proved that when solving one like this, you can just use the standard form. So this is the problem. It often arises in physics. That's the problem there. A great many things in the world behave like that, where the growth rate plus some function times the function itself equals another function. That's how a lot of things behave in physics. And when solving that problem, we have a solution that looks like this. And this is what we call the exponential form. Which states that the solution y of x, that is the function of x we are looking for, is Euler's number raised to the power of minus an antiderivative of f.
Times parentheses the integral of g.
Multiply e by an antiderivative of f. And then plus some constant. And if we choose to multiply, we multiply that factor with the first term and multiply that factor with the second term. Notice that you must not multiply this factor inside the integral sign. That's not allowed. You can only do that with constants. This is a function. Then we get, if we multiply in e to the power of negative capital F of x
Times the integral of g of x. Multiply e into the antiderivative of f. And then plus k.
multiply e to the power of minus uppercase f. So the only thing I've done is multiply that factor into the integral and that factor into the constant, and then we get that.
Now we can see the solution structure, as this is it.
This, we proved that last time. I don't know if you remember, but we did it last time. We proved that it solves the differential equation. So it is a particular solution. It is one and only one specific solution given here. We call it yp,
A particular solution.
And this one,
We showed that last time as well. It is the
Solution.
exact closing
Corresponding
point.
homogeneous equation.
So this is the complete solution.
make it uniform.
And addition.
And that can definitely be asked about in an oral exam, meaning you need to be able to recognize the structure. So how did we get there again?
This one for this solution.
Oh yes, we got a good idea to multiply by Euler's number raised to an antiderivative of f. That's called the integrating factor. Let's quickly repeat the proof again.
Male?
EE står ved.
Why? It is proven to be a smart choice.
So if I multiply by IF, I get IFs, the first step, which was in progress, plus extra. Multiply the second term, which is called f of x times y. And on the right side, I also need to multiply by e prime f, so I get e prime f times that was the first step. And then we discovered, while doing this proof, that everything written here, it can be written much more elegantly. It can be written like this. And it is always exactly here that people, if they get nervous during the exam, this is where it happens if they draw this question. It's about explaining that. So let's explain it again to be sure you're following. Why is that the same as everything written up there? This is because if you differentiate a product with respect to x, you need to use the product rule. But the product is not just a product, it is actually a product of two factors, one of which is a composite function. So you need to use the chain rule within the product rule.
So you need to be good at
Here
differentiating.
you will see it. And that's why having a good memory helps. Because if you know what should be here, it's not so difficult to show that it's true. But sometimes it can be hard if you don't have a good memory to recall what should be there. And this is where mathematics is not something you learn by heart, but it really helps a lot if you're good at memorization. Because everything that isn't calculation has been memorized. That way you can explain the rest. So what do I get if I differentiate this? Differentiate the first times the second remains unchanged, plus the first unchanged times the second differentiated. And that's how you differentiate a product. So what does E capital F differentiated give? Well, E capital F differentiated, it gives itself. But since it's a composite function, it doesn't just give itself. It gives itself times capital F differentiated. And capital F differentiated by definition is lowercase f. If you differentiate capital F, then you get little f, because big F is an antiderivative of little f. So when I say capital F differentiated, I get capital E capital F times lowercase f, as it says here.
Ah, that's also what it said there.
So this entire term is what you get when you differentiate the first factor and multiply it by the second factor unchanged. There it is, bang. Plus, then I leave the first factor untouched, e, and multiply by the second factor differentiated. That's exactly what's written there. Now I've explained why that is exactly the same as that. And that is Roman calculus rules 3 and 5. While calculus is being repeated, I use that here.
And now we are happy because there's something about differential.
What does that yield? So we can find that using the bind ticker. Then we will integrate both sides. And if we integrate here, then d dx disappears because it's the reverse of integrating. So the inside survives and gives e to the power of capital F. And then I just need to integrate over here on the right side. So the integral appears. The integral is e to the capital F. Okay. And then plus k. And that was the constant I mentioned, where some wait to say plus k until the day they calculate the integral. We write it right away so we don't forget it. One could also argue that it should be included now, because when we integrated this part, a constant also appeared. It's just been moved over to the other side of the equation. So I usually write plus c here. And now I will try to lift the board, but it can't be lifted.
Because we're inside this awful room.
And to find y, I need to remove this factor, which is done by dividing by it, or multiplying by its reciprocal. The reciprocal is e to the power of positive capital F, which is e to the power of negative capital F. Therefore, we have that y equals e to the power of negative capital F. Multiply, and since there are two terms here, remember to put a parenthesis, and you cannot just use a big parenthesis, or a square parenthesis, or whatever you feel like. And then the integral of e raised to capital F times g.
From x to x and plus.
And then if we multiply that with the integral and that with the constant, we get what I've written here. And then we are in a bowling alley.
Now we have the tank shape.
I'll just write G first. The order of the vectors doesn't matter. and then plus k times e to the power of negative capital F.
And now see how easy it is to explain in an exam
Thank you all.
that this is what works with homogeneous equations.
Because if it is homogeneous, what is G?
Then it's homogeneous, you know? That's what it means to be homogeneous. That's if there's a zero over there.
And if G is 0, then it multiplies by 0 here.
And then the whole first term disappears. And then there's only that left. So if you can't remember which one is the homogeneous one, just imagine that G is 0. Then you can see it. Because this entire factor gets multiplied by 0, it disappears.
That was the first part of the rehearsal. Then I showed it 2. I showed it 2.
You can prove that this is actually the solution to this problem. I don't know if you remember, but I proved it last time using a method called separation of variables. And you need to use that in your take-home assignment. I'll also make sure that you've seen it that time. On board number 3, so what if there is 0 over there? Well, then it says we have a homogeneous differential in 1. The homogeneous version looks like this. Here, E prime plus f of x times y equal to 0. And I would like to prove that the solution to this is not the full general formula. It is only the last term. It is just k times e to the power of negative capital F. That is the solution.
This is it.
Absolutely. And we can just prove that because then we will learn a technique called separation of variables. So to prove that, we start with a differential equation and see if we can find y. Can we isolate y?
It says Y mark.
Plus for example times y
Equal to 0.
but y prime is the same as dy dx. It's just another notation for the same thing. So instead of y prime, I can write dy dx.
In
Then you
reality,
can prove that d divided by dx is the same as y prime. But unfortunately, that is outside the syllabus.
so plus f of x times equals 0.
Wow.
That's how you do it.
My proof is called the separation method.
Are they variables? Then you separate the variables. You take everything related to x and place it on the right side of the equal sign, and everything related to y stays on the left side of the equal sign. And this is done by starting to move this term to the other side by subtracting it from both sides of the equation. Then it becomes dA over dx, nonetheless, minus f of x times y. And now you can see that I've moved something with x over to the right side, but there's still a y here, which I don't like because I want it separated. So I want to divide by y on both sides, so y disappears. And then I just need to mention to the examiner that if y is not 0, then I am allowed to do this. So if y is different from 0, then I am allowed to do what I am doing now, which is divide by y, and I cannot divide by 0, as that would make the universe explode.
So now it will say that so it's just minus f of x.
Times dx, so I see times dx over there, and then I should divide by y, but it's the same as multiplying by 1 over y. So it says 1 over y times da equals negative f of x times dx.
So separated, meaning divided into variables.
And then you integrate on both sides. So on the left side, I integrate 1 divided by y with respect to y. And on the right side, there is a cigar. Minus f of x with respect to x. And note that I just put the minus outside because it is a constant. And when we perform that integral, a constant appears, an integration constant. And you could call it little k, but since little k is what I need to end with, I'll just call it little c, for example, instead. It's just a constant. And then we start solving that integral. What is the antiderivative of 1 over something with respect to that something?
Of the absolute value of that something. So here is the natural logarithm of the absolute value of y. And why should it say numerical? Because you cannot take the ln of something negative, and I don't know if y is negative or positive. The only thing I know about y is that it's not 0, and that's what I've assumed. And on the right side, well, I can just find the antiderivative of f, that's capital F, and then plus c, and c is some real number. Then I can find the numerical value of y by removing the ln, and I remove ln with its inverse function. So I exponentiate both sides with Euler's number. So I get Euler's number raised to the ln of the numerical value of y. I have erased to the power of negative antiderivative of f now c. And I hope you can see that I'm getting something that looks like what I needed to prove. It's close now, because you can see that these cancel each other out, so now I am there. I have isolated not y, but the numerical y. So what I now have is that the numerical value of y with this. And it can be written like this as e to the power of c times e to the power of negative capital F of x. This can be expressed using an exponentiation rule. And that there, well, it's a constant. Because if light speed c is a constant, then e to the power of c is also a constant. But the difference between the constant c and the constant e in the c's is that c can be any number, but e in the c's can only be positive. Because Euler's exponential function, its graph looks like this, you probably remember. This is e to the x, so e to the x is always greater than 0. And therefore the EC values will always be greater than 0. So in such proofs, if you want to avoid getting stuck on some tiny insignificant detail, you really need to have a good grasp of all the math leading up to what we have now. For example, that e to the x maps only positive numbers. Now, so this is a constant. I could call that capital K, so that's what I'll do. And I know it can only be positive. That's how you write it. So now I have that the numerical value of y is equal to capital K times e to the power of negative capital F. Now I just need to get my numerical sign removed. And if the numerical value of something I don't know must result in something, then what I don't know must be either plus or minus. It's something. If I think about it, the numerical value of a number I don't know must result in 5. What is it then?
Either x has to give 5,
I'm not
or
supposed
else
to give negative 5. So in the same way here, if the numeric value is a function I don't know, I need to give that function, then the function must be either plus or minus that. So I find that y, it becomes either plus or minus capital K times e to the power of negative capital F. But I know about K, that it can only be positive for what I've written up here. But now there's either plus or minus K, so I can take plus and minus with K and absorb it into a new constant, which I call little k. And of course, it's no coincidence that I call it small k, because then it matches with what I'm asserting. So I just call it lowercase k. Then I get that y is lowercase k times e to the power of negative uppercase F.
And what about the small k? I can be both positive and negative.
Can it be 0 as well? Actually, it can. And then I also get the solution I skipped over here. And if that constant is 0, it says that y is equal to 0. And is it a solution to my differential equation that y equals 0? Yes, it is. And now let's have a look here. So it is correct that if you differentiate 0 and add it to f of x times 0, you get 0 for any value of x. Well, yes, it does. Because if you differentiate 0, you get 0. Since y equals 0 is a horizontal graph lying on the x-axis. And that slope is 0 everywhere. So y prime is 0 if y is 0. So here it says 0 plus some function times 0, which is always 0. Therefore, I can now conclude that k can simply vary freely over all real numbers, including 0. And then I have the complete solution. So, what is this? It is the complete solution to the homogeneous version of the original differential equation. Any questions? So you can just calculate a little example over here without using the formula. It's really quite easy.
Example, let's invent a differential equation there.
Let's say it says y mark plus x squared times y. It isn't with 0.
What kind of differential equation is it really? It is a homogeneous differential equation, and it is linear and first order. So I can directly plug into the formula I just proved there. The complete solution, y equals x, is equal to some constant that can vary freely. It can be any real number, times Euler's number raised to the power of minus the antiderivative of that function there, which is f. And the antiderivative of x squared is 1/3 x cubed.
And free from cooking methods.
And here are all the solutions. Every k you can think of putting in there works. Put 7 in, and you'll get a solution. Put 13 in for k, and you'll also get a solution. Set k to 0, and you'll also get a solution. It's called a zero solution.
It is the monotonous, trivial, pointless.
All right, we can continue for just 10 more minutes. Let's take a break. The next thing I need to go over is what happens if you're really lucky and they are just constants here and there. That happens sometimes. For instance, it happens in Newton's law of cooling, which can describe a cup of coffee cooling down. It's just constants.
So we can just take a look at that and review it, and then the new stuff will come.
And if you're sitting there thinking, how am I ever going to learn everything else for the exam? Well, I have the answer, you know. You just need to start practicing. It's not as difficult as it seems. But if I manage to learn it, then you can too.
Cool, can you?
Yes, I can too. And that is how he starts the math book I told you about, the professor. What one fool can do, another one can. And since I am a fool, you can do it too. It was really cool, not so pretentious. It's just to get it practiced. Is it actually 4? Or did I forget to correct the number? I can't remember. Did I just correct it? Well, I can remember that far back.
What if you have a differentiation where it says y prime at times y equals b?
Well, then it's just a peculiar case.
It's a special
In
case.
case of
That you want
checking it out, right? Look,
sole case.
so here we can conclude that what is written there corresponds to f of x, and what is written there corresponds to g of x. We don't need to start from scratch, we just need to plug it directly into the standard form. I'm curious about how AI translates the Danish pronunciation. We'll plug it straight in.
Hello?
Then the solution comes out. And it looks like this. Y of x was equal to...
E minus f.
You might as well memorize this formula. Because if you can memorize it, you'll just be terrified when you have to explain a little revenue. So a to the power of negative capital F times the integral of g in parentheses times a to the power of plus capital F.
And then plus some constant k.
Let's just try plugging it in. And now I know what f of x is. It's just a constant. So a and b here, a and b, they are just real constants.
It could be 7 and 13, for example.
So if we substitute it in, we get e is raised to a negative antiderivative to a. Well, the antiderivative of a constant is the constant times x. Because differentiating 5x gives 5, differentiating 7x gives 7, differentiating x gives a. And then we multiply by a parenthesis the integral of g, but g was b. B times e to the power of plus x.
And now you just need to remember to change the sign.
And x, because integrals always end with the symbol dx. And then plus k. So therefore, it doesn't make any sense to ask what happens to dx in a moment. Once I have integrated, because dx is part of what is asking me to integrate. So once the question is answered, you don't ask the question anymore.
One also doesn't answer. What's your name?
What's your name? John. That's not how you reply. You just say John if your name is John, so that dx will disappear shortly when I answer this integral. So let's continue the calculation. This is copy paste. E to the power of negative x. B is a constant, so I
Set
must
it outside when I integrate, so it just remains there.
EIX integrated gives itself, almost. Because e to the power of ax is a composite function. If you differentiated it, you would multiply by a at the end. This is because the modified function is called x, but I am not differentiating it, I am integrating it. Therefore, I should not multiply by a, I should divide by a. See? Now the x is gone. Why? Well, because this is the answer to the question stated from here to there. So, of course, the x is gone. The question disappears when I answer it, and then plus k. And then I can take that factor and multiply it into the first term, and that factor and multiply it into the second term. And when I multiply it with that, I get something very beautiful. Because e to the power of minus x times e to the power of plus x gives e to the power of 0, which is 1.
So it just becomes the main part of the brew when I multiply in.
B squared. And then I multiply that into k, so plus k. Multiply e to the power of minus x. And k is some arbitrary real number. So this is the solution to that differential equation. So we can turn it up to the conclusion. E is therefore equal to b squared
Plus k e minus ax.
I remember when learning about differential equations in the beginning, sometimes it's hard to distinguish between what the problem is and what the solution is. Some people, when they get to this exam, start by saying, I would like to talk about the first order linear differential equation with constant coefficients, and then they write that out there. Not exactly. This is the solution to the first order linear differential equation with 2 constant coefficients. This is the beast we need to solve, and here is the solution. That means if you apply some physics to a cup of coffee that is cooling, where does the physics end up? There. Okay, so what is that down there? It's how the temperature of the coffee changes over time. That's the solution. One needs to distinguish between those. What is the problem and what is the solution? So here comes an example. And if you'd like, I can try to make a cup of coffee example while you take a break, if you want to see it with some real physics. So right now, I'm just coming up with some numbers because I need to think over the other a couple of minutes so it becomes somewhat realistic. But if we have a differential equation called dy dx, now it's 3y,
I am equal to 8. What is it then?
well, it is a first order differential equation, and it is linear, and it has constant coefficients. So just like per your request there. And note that sometimes the problem setter might disguise it. For example, they could put 3y over on the other side, so it reads 8 minus 3y. Then you can just notice that if you rearrange it, it resembles that structure. And that's why one says that a differential equation that can be written in that form, it might not be written in that form, but if it can be transformed into it, then that's the solution.
So I will state that this is A and that is B.
And then you just plan it, you know. I'm not supposed to say that, so it's just about plugging it directly in down there. So I get that y, which is some function of x, is b divided by a, that is 8 divided by 3, plus the constant k that was there,
Raised Euler's number to
minus 3x, where k can be any real number. This is the solution. So let's take a break, and then I'll try to show you what it might look like when cooling a cup of coffee. So you can see how the graph looks, giving you a sense of what you have found.
So let's say we take a 10-minute break, and then we'll start again.
So you had a break, and I promised to show you a practical example from the real world of where the differential equation appears. And once I've done that, You'll see why mathematicians typically don't create many of these types of examples. It's because it only gets harder when you have to use it. And that's why mathematics is usually a subject on its own, where you start by doing math and later learn how to use it. It's actually harder for most people to apply it. Some people also say, now I understand it because you gave an example. Oh, how cool. But usually that's a form of advanced self-deception. You don't understand it any better. You just see why you need to learn it. So now comes an example. And it's an example of a cup of coffee cooling down. Let's see if we can get a differential equation that resembles the one above. And that must be pen 05. So the headline is Newton's law of cooling. Newton's cooling law. The story is that you should imagine having a cup of coffee. It might be a thermos with coffee in it. And it has been refueled at some point, and you need to keep track of its temperature. And since there are both temperature and time in this story, I run out of the symbol T. So that's why I use T for temperature.
And I use tags for time.
There is a ticking sound. So this cup of coffee here, right when we pour it, we do it at time 0. So at time 0, we pour in the coffee. And then there is the temperature, which is called T0. It means the temperature at time 0. And let's say the freshly brewed coffee is maybe 80 degrees Celsius. Isn't that about right? I don't drink coffee, but I think it's around there. Otherwise, it might be a bit sad right from the start. And then you just place this cup of coffee on a table and let time pass. And the ambient temperature plays a role because that cup of coffee, as we all know from experience, eventually ends up at a temperature very close to the ambient temperature. In principle, you would have to wait indefinitely. In practice, you don't have to wait terribly long before you can't taste the difference between the ambient temperature and the coffee. So let's say the ambient temperature, which I'll call T sub S and stands for room temperature, is set to 21 degrees Celsius, just as an example. And without solving any differential equations or anything, I can plot in a coordinate system what we expect to happen. Imagine we have a coordinate system where I measure time along the x-axis, but it's not time t, it's time tau, sorry. And I measure it in seconds. And along the y-axis, I measure the temperature of the strength T, and I measure it in degrees Celsius, and that's how physicists also write it. Write the physical quantity divided by the corresponding unit of measurement. The physical quantity divided by the corresponding unit of measurement. That's how we should label the y-axis.
Oh, wow.
And then we know that when the time was 0, when tau was 0, the temperature of the coffee was 80 degrees Celsius, so it might be around here.
So imagine that this right here is AT, right at that spot.
And then time passes and the coffee's temperature decreases. However, the temperature of the coffee never becomes cooler than the ambient temperature. So I just need to mark the ambient temperature at 21. It's maybe around here. 21. And here I draw a horizontal dotted line. Because I know that as time passes, the coffee temperature will get closer to that line. So I get something that looks like this. That's the temperature of the coffee as a function of time. And this horizontal line is called a horizontal asymptote. It's a straight line that the temperature graph goes down to and gets close to, but never really reaches theoretically. In practice, it might, maybe. It's actually a philosophical question. Is there a smallest temperature change? We don't know. So it's something I calculated as if things were continuous. Here is a horizontal asymptote. So the question is, how do I actually arrive at a differential? Because I can almost figure out that this is how the world behaves. And you think about it like this. The rate at which the temperature of the coffee changes over time, that is what's normally called dy dx in mathematics, or y prime. But now, because we are in a physics problem, it is called dt dt. This means the rate at which the temperature T changes as time progresses. And that is a slope coefficient. And if you look at my graph here, you can see that there is a negative slope everywhere on the graph because it always goes downhill and the coffee is always cooling. So I probably have to put a minus here because it always goes downhill. And then there's probably some constant I need to include, which tells me something about how good the heat transfer is between the coffee and the surroundings. It's built into K. It's a kind of insulation level between the coffee and the surroundings. And wouldn't the slopes of these tangents also be, you can almost see it on my graph. They do like this. So there is a steep negative slope at first, and then it becomes less and less, but still negative. This suggests that the slope depends on how far we are from reaching room temperature. So therefore, if I take the current temperature of the coffee at any given moment, and then subtract the room temperature, so I get something that helps model what the slope should be for that process. Can you imagine it? So what it says here is the rate at which the temperature of the coffee changes with time. It is proportional to how far the current temperature of the coffee is from room temperature. And this is called a mathematical model. So I have assumed that the rate at which the temperature of the coffee changes over time is proportional to how much the temperature of the coffee deviates from the room temperature. And if I multiply that by that and rearrange it, then I have a first order linear differential equation with two constant coefficients. Because if I multiply that by that, what do I get then?
Oh, it shouldn't have said roof. It should have said T.
It's T. It's tau, I should write. It's T. It's tau. I equals minus K times T and plus K times tau. And then I can take that term and add it to both sides of the equation. And how do I know that's the term I need to move? I can do that because I've practiced recognizing the structure. And which structure do I need to know? It's this one. I'll write it up again so you can follow along. The structure I need to find is the one that's called y prime plus some constant times y equals some constant.
That's the differential setup we were about to run.
And now I can see that it's time.
There is my function. Then it is the term containing time that needs to move to the other side. So t corresponds to y.
So it will match when I add that part on both sides. Now it will say dt near the tag.
Plus k times t.
So what chance just do it addings?
Now you can see that it has the same mathematical structures here as here. Because what is AMDK? It is a constant. And what is B? It's the constant. And some might wonder if that over there is a constant too. Yes, it is, because K is a constant, and we're assuming the room temperature is constant. Clearly, if there are fluctuations with the thermostats, the mathematics becomes much harder. So we assume the room stays at the same temperature while the coffee cools down. Otherwise, it's a difficult problem.
Not necessary.
So you can see that this corresponds to A.
And everything that corresponds to B.
And we know how to solve that differential equation because we just proved it.
There
E
it
and
was.
X, well, that was the bachelor's thesis of it. Plus a constant K times a E minus a X. So I can use that solution structure to solve that differential equation. So this is just a little reminder box we use to solve the problem. So what will be the temperature of the coffee?
The function is the time, measured in seconds.
Who it will be? B pushed me off, but what was B? It was K times TS. And it must be divided by A, which is K. That was nice. So K cancels out. Plus some constant. Up there it was called K. We can hardly call it that now because there are other Ks. Now I'll call that constant C. I know it doesn't matter what the name is. What's in a name? So C times E and minus A with an A over K times X. But X is not X now. Now we need a time as the independent variable. It's called 2. There you have the solution. And if I just write it out clearly, I get that the temperature of the coffee as a function of time tau, measured in seconds, is equal to the room temperature plus a constant times Euler's number raised to the power of negative K times time tau in seconds.
This is the complete solution. So this solves all problems where coffee cools in a room with constant temperature. But we are in a very specific room because we have created a particular room where the room temperature is 21 degrees. So I can plug that into the equation.
21 the temperatures in our task.
So the question is, in our task, what is little c? We can find it because we know that the temperature of the coffee at time 0 is 80 degrees. So if I put 80 degrees here on the left side, which is a temperature, I just need to set tau to 0, because we know that at time 0 we are at 80 degrees Celsius, and then I can find it. So let's find c. And it's called a conditional solution. It's the solution that is contingent upon what I came up with
Like
here.
that.
There. That is the complete solution because it solves all coffee cooling problems at once. Now you see why we talk about particular solutions, conditional solutions, and complete solutions.
Let's now find the conditional solution.
Imagine that the solution is,
I will put 80 in there.
and here it should say 21. And here there should be something I don't know, which is c times e to the power of minus k times 0. But 1 minus 0 is 1. So now it says that c plus 21 must equal 80. So it must be about 60, roughly 59.
So that means C should be 59.
So c is 59 under the condition I came up with. So therefore c is exactly 59 for the conditional solution. So now I can write down the conditional solution. It is called the temperature of the force as a function of time tau is equal to 21 plus 59 times e to the power of negative k times tau. And already now we can actually see that it looks right if we think about it. Try looking here. If this is the temperature of the coffee, what is the temperature? Where does the coffee end up after an infinite amount of time? When tau is infinite? Well, then it's e to the power of negative infinity because k is a finite number. So when tau becomes infinite, it dominates whatever nk is, no matter how small k is. It will become infinitely negative.
And E in negative migration, that is 0, say physicist.
Mathematicians say that it approaches 0 as tau approaches 0.
And in good turns.
But physicists say it's 0. So that means it's
1 to
59
0.
times plus 21. What is that? 21. So what is the temperature of the coffee after an infinite amount of time? 21, according to the physicist. And the mathematician says the temperature of the coffee approaches 21 as time goes to infinity. Yeah. But for all practical purposes, the coffee is 21 degrees. In 200 years, right?
It's just as boring to drink as if it were 21 anyway.
Well, for now, you just have to find k.
And that k up there, what is that? Well, it's a constant that indicates how quickly the coffee cools. And I haven't told you anything yet that would help find k, so we need to figure that out. For example, you could say that I found out with the thermos I've bought, the coffee is still 60 degrees after 3 hours. And those were the numbers I used here on the board when I was preparing. So I think I'll just use them. Now imagine we know the temperature of the coffee after 3 hours. And 3 hours, that's probably 10,800 seconds because it's 3 times 3,600. I calculated it to be 10,800. I think that's correct. It should be 1,800 plus 9,000. And there I know that the temperature of the coffee at that time is 60 degrees Celsius. And it's actually enough for me to find k, that's up there. And once I have found k, then I have the final solution that matches exactly this cup of coffee and exactly this thermos, with the starting temperature of the coffee and the ambient temperature at 21 degrees Celsius. So now I take 60 and put it in there. And that's the temperature.
So 60 should equal 21.
Plus 59 times e raised to the power of negative something I don't know, which is k, multiplied by a time I know well, which is 10,800. And notice that the only thing I don't know is Landini.dk.
And K measures how quickly the box transfers temperature to the surroundings. So it depends on the quality of the thermocouples purchased.
So now we can find k. So I'll just subtract 21 from both sides here. What does that give? 39. So 39 equals 59 times e to the minus k times 10,800. Now I would like to isolate k. We know up here
Because it's something we know from experience in our history. So we know it's true that the coffee has cooled down to 60 degrees after 3 hours. Well, then I can find K. I just need to divide both sides by 59. Then I get 39 divided by 59 equals Euler's number to the power of negative K times 10,800. There's a smart trick. I'd like to get rid of that minus, so I'll reciprocate both sides. So this fraction is simply flipped, and then the negative sign disappears. E to the negative something is the same as 1 over plus that something. So I have reciprocated that side, and I've reciprocated the other side. Are you following? So now it becomes 59 divided by 39 is equal to Euler's number to the power of K times 10,800. Then I take the natural logarithm on both sides to get rid of Euler's number. So now it says that 10,800 times K, if I just move K to the end, as you normally do with a variable, is equal to the natural logarithm of the fraction 59 over 39. And then I can find K by dividing by 10,800.
So K is on
to 59 over 39 divided by 10,800. And that number I had calculated on my calculator, so I can't compute it in my head. So I had to enter it into the calculator, and I got it to be 3.83 times 10 to the power of negative 5. 3.83 times 10 to the power of negative 5. We measure the rate in inverse seconds then. Now it has become a physics lesson, because I'm giving an example. But why is the unit in seconds to the power of negative 1? It's because take time in seconds. The measurement should be in inverse seconds, so that inverse seconds cancel out with seconds, leaving a dimensionless quantity. And then Euler's number raised to a dimensionless quantity gives a dimensionless result, which scales the temperature. And see, what was it? It was a number of degrees Celsius. So you really need to understand all the physics for the examples to fully make sense. But now, the final solution looks like this. The temperature of the coffee as a function of time in our task is equal to 21 degrees Celsius plus 59 degrees Celsius times a scaling factor, which decreases over time, called E, is negative 3.83 times 10 to the power of negative 5. The reciprocal of seconds times time, and there is the solution. And if you plot the graph for that solution, which I just tried on my calculator, you will get something that looks like this. And I could see that it matched. When it reached 10,800 seconds, the temperature was down to 60. I could see that on the graph.
So it fits, it's fine.
And what can this be used for then? It can now be used to tell what temperature your coffee has at any given moment. Not just what you had measured yourself after 3 hours, but at any time. Assuming that the mathematical model we've set up here matches reality. And it actually fits quite well. We've tested it. I once went down to Biltema and got a small electronic temperature sensor, and then we measured it. And then we could see how well it matched.
And it fit perfectly well.
The rate at which something cools is proportional to the difference from the ambient temperature. That's how the universe seems to behave. What drives temperature equalization is the difference in temperature. That also makes good sense. Any questions about the example? But that's why we learn about differential equations, so we can solve things like that, right? And then there'll be a course later on for all of us, including the biotech students, called mathematical modeling. It's about being able to set those up by thinking, learning some physics, and then using our math skills to solve it. Allah, all right. Now we are going to learn about superposition and the guessing method. Board 6. I can't remember, but I'll write it now. I just need to think of it.
Superposition and the method of images.
And that's what's new coming today. And now we are essentially done with first order differential equations. You could have an entire course just on differential equations, and it could last several years. To really master differential equations, it might take 100 years. I've seen many more that I can't solve than those I can. Even if one took a course for 100 years, there would still be far more unsolvable ones. But fortunately, a solution can appear.
Some of those who call us.
In some way,
One cannot say anything about
yes,
reality.
you can't do that.
One can say exactly nothing.
What I mean about what reality is. But one could say, if I measure reality, what comes next? It's something entirely different to say something about reality. Physics is about predicting what the universe does next. It is not mature enough to tell what the universe actually is yet. But we need to talk about superposition. And the guessing method and that thing about superposition, it's really something that applies very generally, not just in mathematics, but also in physics. And it's such a neat way to express something actually quite simple. It means that if you have multiple things contributing to something, you just need to find out how much one thing contributes, how much the second thing contributes, how much the third thing contributes, and then you just add it all together. So it's just a neat way to say it. I will explain it more mathematically. And the guessing method is about when using the brute force method. Sometimes some rather unpleasant junk appears that you can't actually solve. And then you can, of course, just let Maple or another math program handle it. But you couldn't do that in the old days, and we are in the process of learning all the old disciplines to understand some of the mathematics. In Maple, you can just type dsolve, input the differentiation, and then the solution appears. If Maple can solve it, it can't solve everything, but it can solve more than we can. But the other guessing method involves, if there are ugly integrals, dropping the standard form and guessing the solution. And I will show you that first. We will start with the guessing method, and then you will see what superposition means because of it. It's just a series of examples, really. Let's start with an example that is relatively simple called the y mark.
Plus 2 times y equals 3x plus 4.
What is that? It is a first order differential equation with a constant coefficient and a variable. And that means it can be solved using integrating factors. Just plug it into the template and hope you can solve the integral, then the solution comes out. But we can also take advantage of knowing from the structural theorem how the structure looks. The structure theorem has taught us that a complete solution to this differential equation yf for a full solution consists of two contributions. It consists of a particular solution plus the complete solution to the homogeneous version of the differential equation shown here. And over there, we have created a formula for that.
Can you remember it? The formula to find a complete solution?
To the corresponding homogeneous differential equation. We have just proven that using separation of variables, it was k times e to the power of negative capital F,
Where k is an arbitrary real constant.
we can do that right away.
And you should remember, this here is ff, right? And over here,
So we can do that right away. So I give k times e minus an antiderivative to a total, which is 2x. Hello there. So that means we already have that ingredient under control.
so we only need that one. And you can guess it.
And that is why the method is called the guessing method, which I will show you now.
So we guess now yp.
We guess,
Now, yep. So a particle is loose.
and the trick is that if you have to guess yp, then you just need to look at what is on the right side and guess something similar. And what is written here? It's a straight line ax plus b. So you guess a function of exactly that type. Just think about it. What is written over here? The function we don't know needs to be differentiated and added with 2 times itself, untouched, and then you should get a straight line.
What are the functions that become straight lines if you multiply them by 2? They are also straight lines. What do you get if you differentiate a straight line? A number? What do you get if you add a number to a straight line? A new straight line? Are you following? So if I need to find something that differentiated and added to itself, times 2 gives 3x plus 4, then it's a really good guess to go for x plus b, because it's some kind of straight line. It must be some kind of straight line that has the property that multiplying it by 2 and adding it with a constant results in a new straight line. It must be a straight line. So therefore we guess ax plus b. So we just guess that. And how do we determine what a and b should be? We do that by simply plugging in our GitHub and finding a and b. So now we insert the gas into the equation and find a and b. We insert do you mind? And determine a and b. Okay, hold it. Let's try it then. So first, I apparently need to find the y prime. It's right up here. If y is x plus b, what would the derivative of y be? A. And that's what I'm asking. What is the slope of a straight line A?
So I just need to differentiate this. I provide a and place it there. Then I write a.
Plus 2 times y. So plus 2 times y. But what was y? Well, it was x plus b. So remember to put parentheses because there are 2 terms. And what will that give? 3x plus 4. But notice you should not solve the equation with respect to x. It needs to equal 3x plus 4. I will write it down. And this equation I have written here, it must not only be true for one specific x, it must be true for all x. And remember, a differential equation is an equation for determining a function that makes the equality sign true for any value of x. So the equality must hold true for x equals 7, x equals 13, x equals anything. So how do we solve this? Well, we multiply into the parentheses here, and then it will say 2 times x, 2x plus 2 times b, and then plus a, which is out here. Are you following? It must equal 3x plus 4. But if this is to be true for any value of x, you need to use something called, it sounds very intimidating what I'm saying now, but the fundamental theorem of algebra, which states 2 polynomials are equal for any value of x if, and only if all of their coefficients match. So since it says x plus b here, and it also says x plus b here, essentially, because it's something times x plus something else. Well, then it can only be true if the number 3 matches with this coefficient, and if 2 times b plus a matches with that coefficient. Do you see what I mean? 2 polynomials can only be equal if all their coefficients are identical. 2 first-degree polynomials are identical if their slopes are the same, and their intersections with the y-axis are the same. Just remember, it must hold true for every value to be valid. So we are not solving the equation with respect to x. We are solving it to find a and b. So now we get 2 equations. One equation states that 2 times a should equal 3, and the other equation says 2 times b plus a.
Are all foregoing?
Are you following that? Okay, then I can find a. It must be 3 halves. So a must be 3 halves. So far, so good. Now we are a step closer. But now I know a, so I can find b in line number 2. Because in line number 2, it says that 2 times b
Plus a, but I know a. It is 3.5.
That it should result in 4.
And now I can find d. I subtract 3 halves here. Here it says 8 halves. I subtract 3 halves. That's 5 halves. So 2b equals 5 halves. And then I can find b.
So b must be equal to 5 quarters.
Because you divide a fraction by a number each time I mention it. So 5 quarters. So now I have a and b. So what do I have? Now I have a particular solution. So I'll just add it to the complete solution, to the homogeneous one, before I'm finished. So what is yp? Oh yes, it was x plus b. That was what I had guessed, that it was x plus b. That was my guess. So now I just insert my a there and my b there.
and I had found my A to be 3.5, and I had found my B to be 5/8. Well, now I can write down the solution to the original differential equation. It is called
The complete solution is equal to 3/2.
x plus 5/4 plus k rho e and minus 2x. That is the solution.
And k can be any real number. Now it's your turn to practice a bit.
So in just a moment, I will pause the recording. I just need to give you a task so you can try.
And I'll be nice by giving something nice over here.
And give you a couple more examples so you know what to guess if it doesn't say 3x plus 4. What if it says sine of 2x? That's coming shortly. But let's practice that a bit first. Should we have a picture? Maybe I should write the tasks here so you can see the method. I don't know if I've written notes. Some certainly haven't, but I'll write the tasks here.
So just try to solve these couple of tasks here.
We'll pause the recording here while you try to solve them. Okay, let's just go over the tasks on the board. The two tasks I came up with here. Okay, so we have an equation called, we label plus 5 times e must be equal to negative x plus 2. And the other one, I'll just write it over here so I can erase it. We know minus 3y. Let's go with double speed.
Minus 5. Then I can discreetly handle this.
Okay, let's try to solve that one first.
Well, I talked a bit too much. Thank you, Rune. So here we see that we have a first order linear differential equation with a constant coefficient and a variable. And this corresponds to the f coefficient, and this corresponds to g. In principle, you could just plug it directly into the standard form and find the answer. And you would probably be able to do that here because it doesn't get too complicated with integrals. But let's try using the guess method. And the guessing method involves knowing that the structure of the solution appears in a specific way. We know that the structure is the complete solution, yf, to this differential equation. It is always equal to a particular solution to this differential equation, just one. And then plus the complete solution to the corresponding homogeneous differential equation for this case, where on the right side it says 0. So therefore we can start by finding that one, because if it had just been y prime plus 5 times y equals 0, then we could solve it by separating the variables and using the solution formula I derived about an hour ago. So I here, the complete solution to the homogeneous version is a constant k times e to the power of negative capital F. We proved that. That means I just need to find an antiderivative of 5, and that is 5 times x, and put it here. Then kei minus 5x. That means I'm already halfway. Now I've figured out what goes there. Now I just need a particular solution, and then I am done. And that particular solution is the one you can guess. So we are now guessing that,
And that the particular solution
is a linear function. Why do we guess that? Because the right side is a linear function. Because we know that if you take a linear function and differentiate it and add it to 5 times another linear function, you will definitely get a linear function. Because if you differentiate a linear function, you just get a constant. And a constant added to 5 times some linear function results in another linear function. So I guess a times x plus b. And now I substitute my guess into this differential equation here above to find a and b. So I begin by differentiating my guess. What does differentiating ax plus b give? It gives a.
So it should be placed on the y marked spot plus
5 times my guess y, but my guess y was a times x plus b. And it must be equal to negative x plus 2.
And this inequality must be true for any value of x.
So we multiply out and get 5 times a times x plus 5 times b. And then plus, and it still needs to be equal to what it was before, which is negative x plus 2. And now we can do it like before by comparing the coefficients of the polynomial. Here it says something times x plus something. Here it says something times x plus something. So the part called 5a must equal negative 1.
So we can see that 5 amperes.
It should equal negative 1.
And we can also see that 5b plus a.
That should equal 2. And we can solve this equation immediately. It's just dividing by 5, so we have the a is negative 1/5. So far so good. We have found a... Now we insert it down here and find b. So now it says 5b minus 1/5. It should equal 2. The total can be rewritten as 10/5 when it says that 5b
should be equal to 1/5
plus 10/5. So with 11 over 5. And finally, I can divide by 5. So I have b. Thus, b must be 11/5. So what is our conclusion then? Now comes the important part. So I need to present the entire conclusion. The conclusion is that we can solve the original differential equation that was here by simply following this solution structure. So what is the complete solution yf to this differential equation? Well, it is the particular solution plus the complete solution to the homogeneous version. And the particular solution is negative 1/5 times x plus 11 over 5, because this was my a and this was my b, and I had guessed x plus b. Oh, sorry, 25. Thank you, Rune. That wasn't the number, it was the number that was my answer. And then I should add the complete solution to the homogeneous equation, which is here. So plus k times e to the power of negative 5x, where k is any real number. This is the solution. And that means I should have been able to get it with the integrating factor formula as well if integrals came up that I can solve. So I will just show you. You could have also obtained it with the integrating factor formula. And it's not because I need to give you 10 different methods that are equally good. It's because sometimes it's much easier to guess than to use the integrating factor method. But it might be that in this particular case, it was just as easy to use the integrating factor method. And it might have been a bit pedagogically clever because then I could show you that it also worked. So I hope it works. Let's try using the integrating factor method. And the integrating factor method says, so now an alternative way to do it comes. It says e to the power of negative capital F
times a parenthesis, the integral of g,
multiply e to the power of plus capital F. That is the transforming formula. And in principle, it should work for all of them. As long as they have a structure that is first order linear, then one should be able to use the integrating factor method. It might not always be possible to calculate the integrals, but here I believe we can. So what does it give? E to a negative antiderivative. It gives e to a negative antiderivative of 5. That is minus 5x. Multiply by the integral of g, but g is minus x plus 2. Minus x plus 2.
Multiplied and raised to the power of plus 5 times x.
It is not a house card.
And what does that give us? It actually results in an integral that's not very pretty, because it gives an integral like e to the power of 5x times x.
but we've solved something similar before. So I think we can manage it. I'll just take this integral and solve it separately somewhere else so you can see it, because I probably won't have space down here. So let's do it over here. Let's just do it over here. So we need to solve the integral of negative x plus 2 multiplied by e times m times x. And that's where the guess method is clever, as it allows you to avoid that integral. You'd prefer to avoid it when you encounter it, as it's not exactly easy, but you can multiply in and get two integrals. The integral is negative x times e to the power of 5x. And when I multiply in there, I get plus 2 multiplied by e to the power of 5x. So I have kind of split my integral into two, and I have used the fact that you integrate a sum by integrating term by term. And this integral over here is not so difficult. So it's this one. Okay, I just need to shed some light on this. And I'm not sure if you remember that there's a method called integration by parts. And here I could call this one g and that one f. And this f and g have nothing to do with the f and g from the original differential equation. They are just some f and g I have identified to use integration by parts. And maybe you haven't forgotten the rule, the one that said the integral is two functions multiplied together. Is the antiderivative of the one times the other unchanged, minus the integral of the antiderivative of the one times the derivative of the other?
That rule. We repeated it. What we've repeated is the integral rule.
So I can properly use that to solve that integral. So I need to find an antiderivative for e to the power of 5x, because I need to find an antiderivative for f. And the antiderivative for e to the power of 5x is straightforward if you remember to divide by 5.
So that gives 1/5 of e to the power of 5x.
If you differentiate that, what do you get? 1/5 of e to the power of 5x times 5, and then the 5
And
cancels.
1/5 out. Then you get that.
Then we multiply by the other one, unchanged, which is called minus x.
Then we write a minus because the formula says so.
And then we take the antiderivative, the integral of the antiderivative again, which is still 1/5 times e to the power of 5x. And then I need to multiply it by the derivative of minus x, which gives minus 1. Just like that. I hope you can see now that this is actually harder than the other one. So the guessing method was probably the easiest. What do we get then? Well, here I get negative 1/5 x e to the 5x.
And minus times minus, that is plus.
And the antiderivative of 1/5 e to the power of 5x is 1/25 e to the power of 5x. So now I have solved it. There it was. Let me add this. What does it give? It gives plus 2/5
e5x that should also go down here.
So now I have to take all of that and put it in here, and then I have to multiply it in, and there you have it.
Are you on board with that? Then we hope to get the same solution.
So that gives e to the power of negative 5x times parentheses minus 1/5
X a.
in 5x and plus 1/25
I 5 times.
But I can combine it with this one here, because here I can extend by 5. So here I get 10/25 plus 1/25. That's 11/25. So 11/25 e in 5x, and then suddenly schooled.
And then we multiply. This with that, this with that, and this with that.
And now you can see that we get the right result, because that and that give minus 1/5 x, since the other two cancel out. Minus 1/5 x, and that times that, well, it just gives 11.25. And finally, multiplying those gives negative 5x. And this is the same
That we
solution.
obtain using the get method.
But you can see that you have to be quite good at integral calculus for this to go well. And sometimes some integrals come up that are really tricky, which cannot be solved by hand. Okay, let's just take a quick break. I can see it in your eyes. Do you have any questions, Søren?
Sometimes the easiest question is if there are times when you have to use the armor formula instead of the guessing method. And the answer is that sometimes it's easiest to use the armor formula directly, but the guessing method takes longer. This is if it's a sufficiently simple task. As soon as the right side of the differential equation becomes complicated, the guessing method was usually the smartest because it uses the structure you know. Let's take a 10-minute break and then we'll continue. So we just took a short break and now we'll see what it means for superposition. The superposition is just a nice way of saying the following. If you have a first order differential equation and the right side consists of two functions added together, here it is a straight line and the other is cosine of 3x. Then you can solve this differential equation by first solving it as if it only says 2x plus 1. Then solve it as if it only said cosine of 3x, and then simply add the solutions together. And that's what superposition means. You simply add together the solutions you get from the individual differential equations by first removing one function and then the other function. So that means we could start by solving it as if it only said 2x plus 1. And once we've done that, we find the particular solution as if it only said cosine of 3x, and then we just add it on top. Then we are finished. And that's quite clever, because often the right side is a sum of several functions. Let's start by trying to solve the first derivative version, where it just says y prime plus 2 times y. And we have done that a few times now, so I hope the right side is a linear function. That's why my guess is linear. I am guessing a particular solution that is linear. The complete solution to the homogeneous equation, we have already determined that.
Because we have that.
Proof. It is k times e to the minus.
Just a wave.
We will need it no matter what. And that means it gives k times Euler's number raised to the power of minus 1, integral function to 2, which is 2x. So far, so good. We have the homogeneous one. Now we will find a particular solution for this one. Afterwards, we will find a particular solution for the other one, where this part is gone, and only that part remains. Then we combine all three things, and we're done. This is what the superposition principle allows us to do. So let's find a particular solution to this one. And we guess a times x plus b. And why do we guess ax plus b? It is because the right side is linear. Because a linear function differentiated gives a number, and a linear function multiplied by 2 gives a linear function, and a linear function added to a number gives a new linear function. Therefore, it is a good guess that you can take a linear function and get that. So we substitute and now get here in the y prime position. We get a, because ax plus b differentiated gives a plus 2 times.
Y-axis, but yes, it's x plus b.
And it has to match the right side, which was 2x plus 1. So now it says that 2 times x plus 2 times b plus a. We need to look at 2x plus 1. So we conclude that 2 times a must equal 2, so it must be 1. So we can immediately see here that a must be 1. But if a is 1, then it says 2b plus 1. And that it should equal 1. You can only achieve that by having 0.
So the leg must be 0.
So what do I have now? Now I have the particular solution. It's called x plus b. That is 1x plus 0 times x.
So that was a specific solution for this one.
So I go back to the original differential equation and now look at the case where it's absent. And there is only k.
Remember to triple check.
So I get a differential equation that is y prime plus 2 times y. We need to equal cosine of x. I am not accepting that. And now we need to think about, we have already found the complete solution to the homogeneous version, which was the one where we set everything on the right side to 0. We have found that, it's right here, but we don't need to find it again. Until we have found 2 out of 3 components.
We have found 1, which we need. We have found the particular solution when it is just 2x plus 1. And now we need to find the particular solution when it is just 3x, or cosine of 3x. Then we add all three things together, and we are done. So what should we guess here? Listen for a moment. We need to find a function that, when differentiated and added to twice itself untouched, gives cosine of 3x.
Do you want to know what that function is?
I hope you can see that a good guess is this guess here. It's some constant times in a
3 times.
plus some constant times cosine.
3 times. And why is that a good guess?
Well, of course, that's because what do you get when you differentiate sine? Well, you get something with cosine. What do you get when you differentiate cosine? Well, you get something with negative sine. And you can see I need to write 3 times x here because it says 3 times x there. And that doesn't change when you differentiate. If I differentiate cosine of 3 times x, I still get minus sine of 3 times x. So since I know I need to end up with 3 times x as the argument, there must necessarily be 3 times x in my guess. But you need to have both a sin and a cosine to make it work. Because look at what happens. Y is differentiated and added to itself, untouched, times 2. And to make things work out, so we end up with only a cosine, our guess needs to include both a sine and a cosine. Are you with me on that? So when you see something with cosine of something here, you need to guess both sine and cosine added together, each multiplied by their own constant. And then we'll see if we can determine those two constants. Let's insert now. We insert into the equation in spring. Okay, first I need to find y prime. What does that give? I differentiate a times sine of 3x. What does that give then? No, you can just write it down. Yp prime. What does that give? A is a constant. It stays the same. Sine differentiated becomes cosine of 3x, just like before. But it is a composite function. 3x differentiated gives 3, so I must remember to multiply by that. Where am I with this? Then I proceed to differentiate this. B is a constant. It stays the same. Differentiating cosine, it gives negative sine. It's the same argument as before, 3x, but I just need to remember to multiply by 3. Join in. So all of this now, and it looks a bit overwhelming, but it quickly becomes clear. All of this needs to be put into the spot for the derivative. And plus 2 times y, and in y's place I have to insert all of that, because it is y. And then I simply have to make it work, if it's 3x. I hope you understand my thinking.
So I am now getting 3a.
Now cosine of 3 times x. Minus 3b sine of 3x. That was the derivative, plus 2x parenthesis. And now I need to put a parenthesis, because there are 2 terms. Because in pair.
It's called a times sine to 3x.
Og plus b.
Gang cosinus up to 3 times.
And all of it, what should it result in? It should result in cosine of 3x. That's the requirement. This is up there in the differential. It needs to give. So what do we have? What about cosine? With cosine, we have 3a cosine of 3x, and then we have 2b cosine of 3x. That means in total, I must have 3a plus 2b. 3a plus 2b? That's how many times I have cosine to 3x. Did you get that? So I look here and say, here I have 3a cosine 3x. I also have it here, of course, 3a to 3x.
When I multiply.
And over here I have 2d
Cosmos 3x.
So in total, I have 3a plus 2b times cosine of 3x. I've just factored it out. I've skipped a few steps in the calculation, and I hope that's okay. Well, what do I have then? So I have minus 3b, but I also have plus 2, because I need to multiply the 2 in. Then I have 2a sine, and I have minus 3b sine, so I can factor out sine, giving me 2 a minus 3b.
Thanks sinus to 3x.
There we go. And everything should be equal to cosine.
Up to 3 times.
Well, then I can conclude something. I can conclude that the coefficient there is the one multiplied by cosine. It must match the number 1 that is multiplied by cosine here. That means 3a plus 2b must equal 1. So we get 3a plus 2b. It must equal 1. And what else do we get? We get 2a minus 3b. It must equal 0. Why? Well, because there's no sign over here. Or, if you want it spelled out on the app, it says plus
Minus?
0 times 3x. You just can't see yourself doing that. Therefore, 0 must correspond to that constant. So I get and I need to make it equal 0. And those are two equations with two unknowns. So one could start using matrices and Gauss-Jordan elimination and everything else. But now we just need to solve it quickly. So we'll use the basic method. Let's isolate B in it, for example, or A. It doesn't really matter what we do. We could isolate A in this one. So I find A, it must be 3B over 2. So 3 halves times B. Then I have found A expressed in terms of B. I just want to isolate A in this one. Move 3B to the other side and divide by 2. And then I can substitute it into A's place here. So it becomes 3 times 3 halves B plus 2B. And that must equal 1. Now I can find B. So what does that make? 9 halves.
That results in 9.5 billion.
How many do I have here? 4 halves. B, right, it is 4.5. The other must write 2. And it has to give 1, which means I have 13.5B. If I need to give 1, then B must be 2.13B. I multiply by 2 on the other side, and with 13 there, I have B. So that means B is equal to 2.13B. And now that I found B, I know it was 3.5 times B. So up here, I can go back and write that this must be 3.5 times B, and B was 2.13. So 2 goes out, so it gives 3.13 of it.
So now I've found A as well. It was B. That's it.
Well, then I can actually write up the solution for the entire differential equation by using superposition. It's just all 3 contributions added together. Plus that one, plus 3/4 times sine of 3x, plus 2/3 times k prime, then you have the complete solution. And I will just write it up here, so you get it in a box here. The complete solution to the entire differential equation, the full solution, yf, becomes
That'll be the one.
2 times e minus 2x. We need to include that. Plus, we also need this particular solution here, which is simply called x. And then we need the one that combines sine and cosine. That means we need 3/4.
There is sine of 3x.
Plus 2/3.
Can he join the cuddle? 3 times.
Oh, cool.
Yes, it's quite a journey home.
So here is the complete solution. And that was a slightly more complicated example, but I hope you could see from the example that it's probably easier than using the armor form. Because if you use the armor form, you have to put this into an integral and multiply by e raised to the power of 2x. And then you end up with several integrals you have to deal with.
Are there any questions?
Yes, I can see.
Yes, actually, we use the property that the differential equation is linear, if one were to prove it. And that means that every linear combination of solutions provides a new solution. So it's not that hard to prove, but we've shown with an example, that's how you do it. And that's the level you can expect to explain it up. Yes, I am thinking of writing up a couple of exercises, and then we can sit and work through them a bit.
Yes, I'm just pausing the recording.